Hi folks, welcome back. Been busy with the project, so it's been a wee while since the last video, but here we are, and we're back with some more advanced higher pass papers, and this time it's going to be the turn of quanta and waves, and as usual we're going to Mr. Davies' interactive PDF, and this time we're looking for interference, and we're going to focus in this video on interference by division of wavefront. And these questions are typically about the double slit experiment, and they quite often include the uncertainties questions as well, about handling uncertainties in experimental measurements. So we're going to have a look at the 2017 question and then the 2022 question. Make sure to have a go at the questions first and then come back when you're ready and we'll show you how to work through them. So if you're ready, here's the 2017 question on interference by division of wavefront. And it's question 10. The internal structure of some car windscreens produces an effect which can be likened to that obtained by slits in a grating. And a passenger in a car observes a distant red traffic light and notices that the red light is surrounded by a pattern of bright spots, and this is shown in figure 10a. So it appears that we've got a number of vertical interference patterns, and we've also got a number of horizontal interference patterns, and we have to explain how the two-dimensional pattern of bright spots shown in figure 10a is produced. Well, the internal structure of the car windscreen must contain vertical lines and horizontal lines that are producing this two-dimensional interference pattern, and these lines are behaving like gratings in both axes or both directions. Part B, the traffic light changes to green, and apart from colour, we have to state a difference that would be observed in the pattern of bright spots. Well, we can use our relationship sheet to help us here, because we've either got the higher grating equation or we've got the advanced higher double slit relationship, and this is it here, delta x equals lambda d over d, where delta x is the spacing between the bright spots, lambda is the wavelength of the light, big D is the distance to the screen, or to the traffic light in this case, and small d is the distance between the lines on the windscreen. And if the traffic light changes from red to green, then you should know that the wavelength of green light is shorter than red light. So if lambda is smaller, and small d is constant, big D is constant, then delta x, the distance between the spots, must be smaller as well. So the bright spots in the pattern will be closer together because lambda has decreased, therefore delta x decreases and big D and small d are constant. There's the SQA marking instructions. For part A, the pattern's produced by interference for 1 mark, and that's due to the horizontal and vertical lines on the windscreen for the 2nd mark. And for part B, we used the right hand side of the marking instructions there, we used the double slit relationship, but you could of course have used the higher relationship m lambda equals d sine theta, and if lambda is smaller then sine theta will be smaller because small d is constant. Okay, moving on, part C. An LED from the traffic light is tested to determine the wavelength by shining its light through a set of Young's double slits as shown in figure 10b, and the fringe separation is 13 plus or minus half a millimetre, and the double slit separation is 0.41 plus or minus 0.01 millimetres. And we're also told on the diagram that the distance to the screen is 8.11 plus or minus 0.01 metres. Now we've got 3 measurements here that are all distances, and it's dead easy to get mixed up between these, especially the fringe separation and the double slit separation. So the fringe separation is delta x, is the distance between the bright spots on the screen, and the slit separation is small d, d for double slit, and the distance to the screen is given the symbol capital D, it's a big distance. So there's our relationship, delta x equals lambda capital D over small d, and we're asked to calculate the wavelength of the light from the LED. So let's make a list of all of those measurements first. So the distance to the screen was 8.11 metres. The separation of the fringes or the bright spots on the screen was 13 millimeters, that's 13 times 10 to the minus 3 meters, and the slit separation on the double slit was 0.41 millimeters, or 0.41 times 10 to the minus 3. Now let's sub all of them into the relationship. Let's sub them in before we rearrange, because even though it's lambda that we're looking for, you'll get the second mark just by substituting the values in correctly. So delta x, 13 times 10 to the minus 3, equals lambda times 8.11 divided by 0.41 times 10 to the minus 3. And then if you rearrange that and do that calculation correctly on your calculator, you'll get an answer of 6.6 times 10 to the minus 7 meters. And I'm rounding my answer to 2 sig figs because the measurement with the lowest number of significant figures in the questions was 2 significant figures, although you wouldn't be penalised if you gave your answer as 657 nanometers. There's the marking instructions. A standard 3-mark question for relationship, substitution and final answer. And you're allowed the usual tolerance with your sig figs as well. Okay, moving on, 10 part C part 2, we've to determine the absolute uncertainty in the wavelength. Well, for this we've got to consider the uncertainty in each of our measurements, so I've cut and pasted a little diagram from the previous page here so we can see it all at once. So remember, delta x, that's the fringe spacing on the screen, was 13 plus or minus half a millimetre. Small d, the double slit, was 0.41 plus or minus 0.01, and the distance to the screen was 8.11 plus or minus 0.01 meters. Now we can work all of these out as percentages so that we can compare them and combine them if necessary. So delta x has got a percentage uncertainty of 3.85, small d is 2.44%, and big D is 0.12%. Now the rule is, if any of those uncertainties are less than a third of the other ones, you can ignore them. So we can ignore the uncertainty in the distance to the screen because it's less than a third of the others. And so to get the percentage uncertainty in the wavelength, we need to combine the percentage uncertainties in delta x and small d. And the way that you do that, certainly at advanced higher physics level, is sometimes referred to as the Pythagorean method. In other words, you square them, you add them, and then you square root your answer. So it'll be 3.85% squared plus 2.44% squared, and then square root your answer to get the percentage uncertainty in lambda. Now this relationship is on your relationship sheet, but it's in the form of fractional uncertainties here. In other words, for each measurement that you take, you're taking uncertainty in the measurement divided by the measurement, and you're getting that in a fractional form. You then square all these, add them together and take the square root, and that gives you your fractional uncertainty in your calculated value. But I think it's easier sometimes just to work them all out as percentages and use that Pythagorean method to work out your percentage uncertainty in your final calculated value. Anyway, back to the question. So our overall percentage uncertainty in the wavelength was 4.56%, and 4.56% of the wavelength, which was 6.6 times 10 to the minus 7 meters, is 0.3 times 10 to the minus 7 meters. So we could write that wavelength like this: 6.6 plus or minus 0.3 times 10 to the minus 7 meters. Here's the SQA marking instructions. They've worked them out as percentages: 3.85, 2.44, and the 0.123, which can be ignored. Those two uncertainties can then be combined as shown there, and we get the 4.56%. Gives us our final answer of the uncertainty in the wavelength of 0.3 times 10 to the minus 7 meters. Uncertainties are a nightmare. Nobody likes uncertainties. But hey ho, as Walter Lewin says, any measurement you make without knowledge of its uncertainty is meaningless. So we've got to know what they are, and we've got to be aware how we should treat them. Anyway, part 3. The experiment's now repeated with the screen moved further away from the slits. Explain why this is the most effective way of reducing the uncertainty in the calculated value of the wavelength. Well, the single measurement with the largest percentage uncertainty was delta x. That was the spacing of the bright spots on the screen. So the largest percentage uncertainty is in delta x, but this can be reduced by increasing the distance to the screen, because if you move the screen back, delta x will increase because the bright spots will get further apart. And even though our scale reading uncertainty in measuring delta x will be the same, the impact of that scale reading uncertainty on the measured value will be much smaller, so it will give us a smaller percentage uncertainty in delta x. That's really tricky for 1 mark. There's the marking instructions. Increasing the slit screen distance spreads out the fringes, reducing the percentage uncertainty in the fringe separation, which was the dominant uncertainty. That's a much better answer. That was the 2017 question on interference by divisional wavefront, although most of the marks were for uncertainties. Let's have a look at another one then. Let's have a look at the 2022 paper, and we're going to have a look at question 12. First thing we notice is it's the same diagram. The student carries out a Young's double slit experiment using a helium neon laser, and the student observes an interference pattern on the screen as shown in figure 12a. And in part A, the student records their measurements. So the slit to screen distance, that's big D, is 2.4 plus or minus 0.02 metres, and the slit separation, 0.38 plus or minus 0.01 millimetres. So that's big D on the left and small d on the right there. And using the student's measurements, we have to calculate the fringe separation. Let's go straight to our relationship sheet again then. And delta x is equal to lambda times capital D divided by small d. Now it's delta x we're looking for here. And we aren't told what the wavelength of the laser is, but it's a helium neon laser. And we can get the wavelength of that from the data sheet. If you scroll down the data sheet, there's a table called spectral lines, but within that there's a little table that says lasers, and there's a helium neon laser there. It's 633 nanometers. That's always on your data sheet. So we can write that as a wee reminder on the page. The wavelength is 633 nanometers, and then we can pop all that data into the relationship, substitute it all in. Big D is 2.42, small d 0.38 times 10 to the minus 3, lambda 633 nanometers. So if we pop all of that in, don't forget all your prefixes. 10 to the minus 9 is nanometers. Capital D, distance to the screen, don't mix these two up. That's 2.42 divided by 0.38 times 10 to the minus 3 for the slit separation. That gives you an answer for the distance between the bright spots on the screen of 4.0 times 10 to the minus 3 meters, or 4 millimeters. There's the marking instructions. Standard 3 marker, although you did have to look the wavelength of the laser up on the data sheet. And part 2 of again it's uncertainties. Calculate the absolute uncertainty in this fringe separation. Well, here we go again. We hate uncertainties, but let's put the relationship down from the relationship sheet, or at least a form of that relationship anyway that's got percentage uncertainties in it. There's the actual relationship you want to be using if you want to put the fractional uncertainties in. Anyway, whatever you choose, you're going to have to consider all the uncertainties in your measurements and combine them as required. So let's write them all down again. Distance to the screen, 2.42 plus or minus 0.02. Slit separation, 0.38 plus or minus 0.01. Now, I always work them out as percentages. Much easier to compare them that way. And we've got 0.8% and 2.6%. Now you can be sneaky here, because 0.8% is less than a third of 2.6%, so you could ignore it. And that means that your uncertainty in the fringe separation will just be 2.6%. But let's do it the long way by combining these two percentage uncertainties. So it'll be 0.8 squared plus 2.6 squared. We want the square root of all of that. And if you do that on your calculator correctly, you'll get a percentage uncertainty of 2.7%. And 2.7% of our calculated value of delta x which was 4.0 times 10 to the minus 3 meters, gives us an answer of 0.11 times 10 to the minus 3 meters, or 1.1 times 10 to the minus 4 meters. There's the SQA marking instructions. Again, it's a standard 3 marker, relationship, substitution and final answer. But on the right hand side there, take note, except the rule of 3 applied. The rule of 3 is that if any uncertainty is 3 times smaller than any other ones, you can ignore it, and that's sometimes a little shortcut that'll save you a bit of time and effort. And also on the right hand side there it says accept calculations using percentages. I would always do percentages, but hey ho, that's just me. In fact, I would use percentages with the next part of the question as well. This is 12 part B. The student now measures across 16 fringe separations, and 16 fringe separations is equal to 62.4 plus or minus half a millimetre. And if you work that out as a percentage, it's 0.8%. And using this data, we have to determine the fringe separation. Well, the fringe separation will be 62.4 divided by 16. And that's 3.90. And that will be plus or minus 0.8%. And 0.8% of 3.90 is 0.03. And don't forget to put a unit in your answer, that's in millimetres. Now that's only worth 1 mark, and you could of course just divided the 62.4 and the 0.5 by 16 and got the same answer there. There's the MIs for part B, and notice on the right hand side it says accept the uncertainty as a percentage. Moving on then, part C, state whether more confidence should be placed in the value for fringe separation obtained in part A or in part B. Well, more confidence is in part B because it's got a smaller percentage uncertainty. In part D, the student now repeats the experiment using a laser that produces light of wavelength 532 nanometers and state the effect that this has on the fringe separation. This is very similar to the question in 2017, but let's put the relationship down again. Delta X equals lambda capital D over small d. And if we now use a laser that has got a shorter wavelength, then lambda will be smaller, and if the distance to the screen of capital D is the same and the slit separation small d is the same as well, then delta X must be smaller. So the fringe separation is smaller, or the fringe separation has decreased. There's the marking instructions for those last 2 bits then. And similar to 2017, most of the marks here are for uncertainties. That's it for this video, but in the next one we are still going to be looking at interference, but we're going to have a look at thin film interference and interference by division of amplitude. So that might be the air wedge or anti-reflection coatings, but that's for another day. See you in the next one.